supersymmetry is your favorite model beyond standard model. And what is the second best one?
Supersymmetry.
Okay, there's no doubt, supersymmetry.
I guess the next obvious question is whether the supersymmetry model you have in mind can fit on your T-shirt. Yeah. So, like you were saying, there are models like now you can predict 125 GeV Higgs and other stuff as well. But now, if the model gets very convoluted, there are always a huge parameter space you can try to fit the data. Is that what you envision, or do you believe there's some kind of reductionism? And also another question is that, do you believe, well, the universe might actually be like a satchel? So we actually found what we predicted.
So as far as supersymmetry is concerned, supersymmetry itself is, as you well know, an incredibly simple theory. And I could write down the minimal supersymmetric extension of the standard model, on the T-shirt. Right? That's not the problem. The problem is that supersymmetry cannot be exact. Supersymmetry has to be broken in some way. In the same way that you give masses to the W and the electron, you have to give masses to some of the unseen supersymmetric particles. And that's the problem. And that's where you guys, working on string theory, have to tell us how it's done, right? So, all that we can do is try to analyze the parameter space of possibilities. But as you say, it's an enormous parameter space. I think we need more theoretical guidance in that respect. And what was the other question?
Oh, are you going to utter the A word?
No. Okay. I'm not even going to say what the A word is. Okay.
Yes.
You said that we should not look into the Higgs, and we need to look into the Higgs. And so what else do you suggest we should not look further so that we can look into afterwards? Okay. Because you mentioned that people should not search for the Higgs particle, but we really look in, we try to experimentally try to search for the Higgs particle.
Right.
So what else you suggest we not to look at?
Okay. Well, I don't know. I did suggest that people look for the gluon, and they did, and they found it. So win a few, lose a few. Well, I've also suggested looking for other things that people have not found. So I think I've pretty much covered all the bases, suggesting things that they should look for and they did find, things that they should not look for and they did find, things that they should look for and that they didn't find.
A number of papers recently have reported finding a gamma ray line at around 125 GeV coming from the center of the galaxy. And I don't know what the speculation is as to what, if this is dark matter decaying and it's got a 125 GeV mass and it's the same mass as the Higgs. How does this?
Okay, well, first off, I think that evidence has gone away. So that original report was some guy who was analyzing data from the Fermi satellite. And the Fermi guys, analyzed it, and the effect was not so significant. And they also demonstrated that you've got the same line in gamma rays coming from the Earth, which doesn't make any sense from a theoretical point. So there were indeed ideas that it might be due either to the annihilations or the decays of particles. But I think the fact that it was kind of similar to the Higgs mass was just coincidence. Anyway, I strongly advise that you sell any shares that you've got in that particular signal.
Other questions from students?
You mentioned that the Higgs field is homogeneous and isotropic, and why it should be so?
The guy just muttered. Yeah, it's a scalar field. So that's actually one other key difference between the Higgs field and the electromagnetic field or the gravitational field. The electromagnetic field is a vector, right? We know that magnetic fields have orientation, like think iron filings. There's no such corresponding iron filings for the Higgs field. The gravitational field, we learned from Einstein, that's actually spin 2, it's a tensor field, so it's even more complicated. So the Higgs has no intrinsic direction. You could, on the other hand, ask, well, okay, maybe it doesn't have a direction, maybe it has a source. Okay. So in some sense, every individual particle acts as a source. Right? But there is this uniform background field which corresponds to the theory sitting in its lowest energy state. And that is uniform and homogeneous throughout the universe. And the fact it's scalar means it's isotropic.
Okay. When do you think that the physicists will be able to calculate the electron mass?
Oh, well, I leave that to the students. Not in my lifetime. So I did mention briefly this problem of why there's so many different types of particles. And the answer to your question is tied up with that. So if you like, we have a theory of where particle masses come from. We don't have a theory of how big those masses are. And that's your question. So, kids out there, something to work on.
Okay, so some students don't take that as a challenge. Other questions?
Do you think it's possible in the future some guys find a series of everything, then you can start all the theoretic work? Is it possible or is it impossible? You need to work in the future. Nevertheless, thank you.
Well, so there's been a lot of loose talk about theory of everything, and I think I have to bear some of the responsibility for that, because I wrote an article about string theory, I think it was about 1985. String theory of everything or of nothing. So far, it seems to be nothing. But that's also unkind. So I think string theory is a fantastic framework, which is much more powerful than the conventional framework of quantum field theory that we have. Everything that I've described has been on this idea of fields in the context of quantum mechanics, quantum field theory. So string theory gives us a whole new toolkit, which enables theorists to do much more sophisticated things. And in particular, it provides a possible framework for describing all the fundamental forces and quantizing gravity. But I think that we should somehow get away from this idea that string theory is a theory of everything. Maybe it would be better to say it's a framework for everything, but not a theory of everything. Right? Now, as things stand, there is absolutely zero evidence that string theory has anything to do with reality at the fundamental level. People have done applications of string theory for other phenomena, like heavy ion collisions, condensed matter physics, and so on and so forth. But for the specific hypothesis that string theory is, okay, let's call it the theory of everything, I think there's absolutely no evidence. Now, I'm personally convinced that it is part of the fabric of the way the universe works, but we don't have evidence for that.
One practical question: wouldn't it be possible to take the accelerators and above the ground finally? Is there any way, at least for the part of the research, to make the accelerator above the ground? But then you can make larger circle, because you can filter out some of the things. You are really at the large energies. What is the main obstacle?
So these accelerators have to be very, very flat. And as you saw, they're getting very, very big. Right? So you need a very big, flat piece of land. So I think you have to think, I don't know, Australia or Saudi Arabia or Xinjiang. But these are not terribly convenient places to build big technical projects. Right? To build a new accelerator these days, you need thousands of people. And to persuade thousands of people to go off to the deserts of Xinjiang, you could try, but it's going to be tough. So people often think that particle accelerators are built underground because of the radiation. That's actually not the case. For example, Fermilab, the largest accelerator in the US, is on the surface. The radiation that you get from these machines, apart from the interaction points, is actually negligible. So I think the answer to your question is, okay, well, if you can persuade several thousand of your friends, scientists, engineers, technicians, to go off to the middle of a desert somewhere, then that might be the thing to do.
Well, okay, so I think if a student has some question, maybe we'll have a 1, 2. Well, okay, so the challenge is too big. Let's think about it more. Well, okay, so I think we have to thank John for the wonderful talk. Yeah. John will be leaving at 4:30 from here, so we'll, if you still have questions over here or 803, can continue to ask questions.